Okay, here we have an AC DC to AC inverter. It converts 12 volts DC to 230 to 240 AC. It's yeah, it's 12 volts DC to 230 AC. Now this inverter wasn't working because it had a blown fuse. The fuse is right here. It had a blown fuse, and it had a spoiled MOSFET. But well, I soldered the fuse, the broken fuse, and it's now working. But it's not working very well because it had a blown MOSFET. Now these inverters usually have MOSFETs, many of them. Now this is a pure sine wave inverter, so it will obviously have several MOSFETs, so that it can create an oscillating current, and this oscillating current is what is amplified by this transformer right here. This transformer right, this big transformer right here, to 230 volts AC. Now this is how these things work. What you see on this circuit board is primarily an oscillator. An oscillator transforms a continuous DC current to an oscillating current, or an oscillating current. Now it can be a square wave current, it can be a sort of shapes, but it's eventually smoothened out to a pure sine wave, or near sine wave AC. Now when these inverters fail, it's almost always the MOSFETs, these power MOSFETs right here. We have got 1, 2, 3, and the fourth one, which I removed, which had failed. And on this other side there is 1, 2, 3, 4. All these are good, but that one had failed. Now we are going to test this inverter right now and see how it performs, and we are going to test it after we replace the MOSFET, the failed MOSFET. Now what I wanted to show you here is how to diagnose these inverters whenever they fail. Now there is almost always two reasons why the inverter will fail. One reason is a shorted transformer. This transformer here is a primary winding and a secondary winding. Now when the secondary winding is shorted to the primary winding, or when the secondary winding or the primary winding, any of the windings, when it's shorted, sometimes it can be shorted to the primary winding, can be shorted to the secondary winding, or the primary winding can be shorted to itself. When the winding is supposed to be, say, 10 meters, for example, and it's shorted to itself, it becomes a shorter winding. Let's assume this is a winding, and windings are, the wire is usually insulated. Now if the insulator is not perfect and the winding is shorted to itself, it will be maybe the insulator is one here and here, so there is a current crossing from this point to this point, and the winding is shorted like that. So when winding is shorted like that, now the rest of this winding on this side is useless, because the current passes through in here and through in here and to this point, and it crosses over to the other side and out. So the winding is this long. The rest of this is redundant. The other problem that might cause this one not to work is a failed MOSFET. Now, yeah, this is the fuse right here. This is the fuse right here. Whoever was in here probably found the problem, but instead of removing the MOSFET, he removed, or whoever was in here removed the gate voltage by removing this side, by cutting this side of this resistor. This is the gate voltage right here. This is a 20 ohm resistor, and what this guy did is that he cut this side of my autofocus sometimes he cut this side of this resistor, so this resistor is disconnected right here. Well, I don't think that helps, because even if you remove the gate voltage, this is not if it's a good transistor like the rest of them, if you remove the gate voltage, the transistor will not work. It's essentially it's same as removing the transistor. Now, with a shorted transistor like this one, once you remove the gate voltage, I mean, it's still the same thing. The drain is shorted to the source. The current will flow. What I'm going to do is I'm going to show you how to check a shorted transistor, which is very simple. And then we are going to replace it and see how it's going to work. Now I have got a 12-volt battery with me here. Here are the connection to the battery, and I'm going to connect this inverter right now. Now you've got to be careful where the fan is running, everything is working. Now the battery side is just 12 volts, it's not dangerous, but yeah, the output is 230 volts, yeah, and that one could kill. You need to be careful when working with these ones. Now let me check the footages with you, and we will decide. We can now see if it's working or not. Here is my meter, and I'm going to insert it right here. Yeah, and 231 volts AC, as you can see right there. So it's working, but whatever current it's producing, whatever voltage it's producing, is not a pure sine wave voltage because of the missing transistor. If the transistor were here, then things would be different. Now what I'm going to do is that I'm going to replace the fuse and the transistor. So the inverter will still work even when one transistor is bad, but it will be operating at a lower capacity, and it will not give you a pure sine wave. Becoming a big problem right here. Now let me see, focus right there. Yeah, there we have it. It's an IOR transistor. It's an international rectifier. That's the manufacturer, and you can see the part number is IRFB 7440. Now this transistor is particular. The drain current on this transistor is supposed to be a maximum of 172 amperes, and the maximum gate voltage is supposed to be 20 volts. The maximum drain voltage is supposed to be 40 volts. The drain source voltage to be 40 volts. Now I couldn't get this exact transistor, but I thought I would get an higher spec one, which I extracted from another inverter, a broken inverter, and I got this transistor, which is also an international rectifier transistor, and it's an older one, and it's FB 337Z. Yeah, I hope you can see. Let me try and show you. Let me try and yeah, there it is. This is the replacement transistor. It's an FB 337Z, as you can see here. Now this transistor has a gate voltage of a maximum gate voltage of 20 volts. It has a maximum drain source voltage or drain voltage of 75 volts. The other one is 40 volts. This is 75 volts, so I decided to go with this one. Of course, I'm suspecting that it won't let much current go through, but it will altogether work. Now this one is a maximum drain source current of 130 amperes, I think. 130 amperes. Now it isn't too far from 170, but I don't think that is too important, because the transistor is not going to let the current is determined by other parameters of the transistor, and I thought that the voltage between the drain source voltage is more important than the maximum current. And the drain source voltage, the maximum drain source voltage on this one is 75 volts. So this transistor will not break down unless you apply more than 75 volts on it. The other transistor will break down if you apply more than 40 volts on it. So to me, this is a higher spec transistor. Now here we have some fuses. don't know if you can see this. This is these are 25 amp fuses. Now I'm tempted to use a jumper on this inverter, but yeah, I'm not going to use a jumper. I'm going to use a fuse, and these are the fuses that I'm going to use. I guess the fuse that was there was a 30 amp fuse, because the inverter is rated 30 amps on the battery side. On the 12-volt battery side, it's rated 30 amps, so the fuse must have been 30 amps or thereabouts. And yeah, I wouldn't want to use the same fuse, 30 amp fuse, so I will use these fuses. They are from another inverter. They are 25 amp fuses, but there are two of them. There are two of them soldered together. So this is effectively a 50 amp fuse. That's a short. So here we are. This is the gate. The gate. And this is the drain. And the gate is shorted to the drain. It's also shorted to the source. It's also shorted to the source. Now, this is the new one. This is the replacement. That is the gate and the drain. No short. It's open loop. Now, what I'm not going to do is that I'm not going to test for the operation of the transistor. I'm not going to test whether the channel opens when you apply a gate voltage, because I'm assuming that the transistor is okay, because the most common failure mode is a short. The transistor failed first and then the fuse failed second. Now that sound you had right there, that was me trimming the base of these fuses. I had to trim the base so that I can weld them as they are. I can solder them as they are. Now I should be careful not to weld the terminals together. So now here is our prepared fuse. solder 2 wires to it because I do not want to squeeze it in here. It's already very crowded. Yeah, a little bit of insulation using an insulating tape so that naked wires aren't everywhere. I think that is good enough, and we are going to now to install it. Okay, we have our fuse welded. The fuse is right here. Try to show you the fuse. This is the fuse right there. I figured that it's too crowded in here for me to put this fuse. The fuse is quite big. I didn't want it to go down here, and it would be a problem to solder it in there. We have our AC 231. So 31 volts. Not too far from the standard 230. You can see in there the transistors are pressed against the body of the inverter, and that's how they get to dissipate their heat into this aluminum body. Now I have the inverter connected to the lights that I'm working with the computer and the television, set. I have the battery pulled out, as you can see right there, and you can see it's the inverter is working fine. Well, we have the TV right there, and as you can see, the TV is working fine on the inverter power. We have the computer right here. This is a 200-watt computer, and I have got the battery removed. As you can see right there, I removed the battery. No battery. The fuses are working fine. Everything is working fine, and yeah, I think you're done with this one. See you next time. Subscribe and support the channel. I think that see you next time.